right, in example 4, we have a piston. So let me draw a little picture here. All right, so here's my piston. These are the molecules in here in the gas. And we're told that it has a initial volume of 1.78 meters cubed, and that the gas temperature inside here is 20 degrees Celsius. So the gas temperature, the temperature of the gas is increased. We probably have a flame or something, heat source that is heating it up. And so we want to find out the new volume. So maybe I'll draw a new picture. So I'm assuming that it is stretched out to some new volume final, which I don't know. I'm assuming it's going to be bigger because as heat flows in, those molecules are going to be moving faster and pushing on the top of the piston with more force over time, increasing the volume. All right, the final temperature is 80 degrees Celsius. Now we do know that the pressure initially and the pressure finally are the same. And you might be wondering why. Well, we're going to assume that this mass here is the same, right? And the air that is pushing on here is just the atmosphere. And that there's no like friction on the sides here. So therefore, really, the pressure that's exerted on the gas is remaining constant. Okay, so it has the same mass, it has the same atmospheric pressure, so there's not any change in that. So it's just expanding freely. And this is known as what we call an isobaric process when we get into it a little later on in chapter 15. Okay, so how do we solve this problem? We might go PV equals nRT, P initial, V initial, T initial, and then P final, V final, and RT final. And then we'll cancel out what's constant. We know that the pressure initially and pressure finally is constant. We know that there's no gas molecules that are leaking out, so number of moles is canceling out along with the gas constant. So we end up with the volume initial equals over volume final is equal to T temperature initial divided by temperature final. Now at this point, people typically make mistakes. You have to remember that when we're using the ideal gas law, your temperature, all right, which I'm not sure if I've listed in here. Actually, funny enough, I didn't. The temperature here and here, that's the most important thing to remember, must be in Kelvin. All right, you need to remember that. That's a common mistake. You can't use Celsius because remember, like when you're at like 0 pressure, you should be then at 0 temperature. Well, 0 Celsius, you know, that actually would have a pressure, right? So it must be in Kelvin, okay? So that means that you have to convert your temperatures into Kelvin. So for example, let me rewrite it up here. Volume initial, we'll write as 1.78 meters cubed, okay, equals volume final over here, which we don't know, okay? And for the temperature, we're going to write 20 plus 273, because that's going to be in Kelvin. And then over here, similarly, we're going to have 80 plus 273 in Kelvin. So I get 1.78 meters cubed all over 293 Kelvin equals volume final all over 353 Kelvin. So the final volume is going to be a ratio of 353 all over 293 multiplied by 1.78 meters cubed. And that gets you a final volume of approximately 2.14 meters cubed. And that's it for this example.